Good morning. Hello everyone. This is Jaswinder Kaur and I am here to teach some theorems on poles and singularity. Thank you. Before starting the theorem, there are some remarks which are very important to recall. The first one is very important. Suppose fz has an isolated singularity at z equal to z0. Then z equal to z0 is a removable singularity if and only if limit z tends to z0 fz exists finitely. So for removable singularity, the limit should be finite. And z equal to z0 is a pole if and only if its limit is infinite. That means limit z tends to z0 on fz should be infinite. Then is an isolated singularity that is neither removable nor a pole is said to be isolated essential singularity, right? Then is a point z0 is said to be an isolated singularity of a function fz. Now what is the meaning for the isolated? Alone, right? So if fz is analytic at each point in some deleted neighborhood of z0, deleted neighborhood means the point except z0, all those points of neighborhood of z0 should be analytic except this z0 point, right? So the function should be analytic at all the points of the neighborhood of z0 except z0 is your isolated singularity. Then this is also very important. If principal part of fz at z equal to z0 consists of no term, then z0 is said to be removable singularity of fz. Now this is a definition of removable singularity in terms of the principal part of the function. So if its principal part doesn't contain any term, that means we are saying that z0 is said to be your removable singularity, right? If fz represents a Taylor series, then coefficient of z minus z0 the power m minus 1 is equal to phi m minus 1 z0. This is your m minus 1 derivative, right? Over m minus 1 factorial. So this is how we calculate the coefficient in Taylor series. If the power is m minus 1, then that means you have to differentiate phi of z0 m minus 1 times over m minus 1 factorial, over its factorial, right? Now let's move on to the new theorem. This is very important one. If fz has a pole of order m at z equal to z0, then the function phi defined by phi z is equal to z minus z0 the power m fz has a removable singularity at z equal to z0, first thing, and phi of z0 is a non-zero. Also residue at z0 is given by phi the power m minus 1 z0 over m minus 1 factorial. Now we have to find the residue at z0 to be equal to this, which is also a coefficient of Taylor series z minus z0 the power m minus 1. And I have also to prove that this phi z has a removable singularity at z equal to z0. That means I have to prove that its principal part does not have any term, right? There is no term in the principal part. So from that it's proved that it's a removable singularity at z equal to z0, alright? Now what is given to us is that fz has a pole of order m. This is given to us, right? So let's start, and we have to define our function phi z to be z minus z0 the power m f of z. We have to define phi z to be equal to this. Now let's start the proof. Now since fz has a pole of order m, so we have, I'm so sorry. Alright. Since fz has a pole of order m, So we have f of z is equal to summation n going from 0 to infinity an z minus z naught the power n plus b1 over z minus z naught plus b2 over z minus z naught square up to, because the pole is of order m, so we have to stop here, bm over z minus z naught the power m, and mark this as your 1. It's fine? Alright. Now when you take the denominator all over, the denominator is z minus z naught the power m, and then take this denominator to the left hand side to the numerator, right? Now also I'm having a circle. When I'm having the circle z minus z naught, which is centered at z naught, having the radius r, which is positive, and of course bm is non-zero. Bm is your last term, the numerator of the last term. Now when you take the denominator, that is z minus z naught the power m, if you take the LCM, the denominator is z minus z naught the power m, and take that denominator to the numerator of the left hand side, and you will be getting 0 to infinity an z minus z naught the power. Now what is my first term? It is n, z minus z naught the power n into an. Now when you take the LCM, it will be z minus z naught the power will raised to n plus m, right? And for the second term, it's b1 z minus z naught the power m minus 1. Because if z minus z naught comes to the numerator, the power is minus 1. And then with the denominator, the power will become m minus 1, right? So we have over here, it is n plus m plus, then the summation, then is an, b1. Z minus z naught the power m minus 1. Then is b2 z minus z naught the power m minus 2 up to so on. The last term is bm, where bm is non-zero. You have to write this for this step also. And let's take this, because it's in the theorem, it's given that you have to take this factor to be equal to phi z. So let's take this phi z to be equal to f of z, z minus z naught the power m. Very fine. And mark this as your 2. So this implies I'm having phi z to be equal to summation n going from 0 to infinity. Put phi z instead of this. This is z minus z naught the power n plus m plus b1 z minus z naught the power m minus 1 up to so on, and the last term is bm. Mark this as your 3. Where bm is non-zero. Now what if if I take my point to be z equal to z0, at z equal to z0, first term will vanish, second term vanishes, and we are only left up with bm, the last term. So at z equal to z0, phi of z0 is equal to bm, and because bm is non-zero, as bm is non-zero, my phi of z0 is also non-zero, right? So then if this happens, then the expansion in 3, this, of phi z, is valid throughout a neighborhood of z0, including z0 itself. Now if suppose this is your circle, this is your point z0, it's the neighborhood of z0, and because of 3, the expansion of phi z is valid throughout the neighborhood and also including this point z0, because your function phi z at z0 is also non-zero, right? So the series in 3 is actually a convergent power series, right? So 3 implies series is the power series which is convergent. Series is a convergent power series. Now because it is convergent, that means your function phi z is analytic, right? This implies phi is analytic at z0. Now is phi z is regular or not? If phi at z0, see phi at z0 is bm, is it regular? Regular means it is having only a regular part. Is there any principal part over here? No. So that means phi z has a removable singularity at z0. There is no principal part. So at z0, phi of z is having your removable singularity. So the first part is proved. Now phi z becomes regular at z0 as phi of z0 is equal to bm. So there is no principal part. And whenever I'm having no principal part, any term, principal part is having no term, that means it is a removable singularity. Hence, phi z has a removable singularity. At z0, right? So by definition from 2, what is 2? We have marked phi of z to be equal to fz z minus z0 the power m. Now for from the 2 we get phi of z0 is equal to, we have to put limit z tending to z0, z minus z0 the power m fz, right, which is simply equal to bm. And let's mark this as our 4, because phi of z is actually bm. We have just calculated that phi of z0 is bm, right? So can I write my bm to be equal to this limit? Yes, yes. Mark this as 4. So this limit always exists and is non-zero since bm is non-zero. So this limit always exists and is non-zero because Bm is non-zero. So what follows from 1? It follows from 1. Now at z tending to z0, what is your first? This is your first expression, that f of z is equal to this. Now at z tending to z0, what is your fz? If z is tending to z0, first term vanishes, but rest of the terms will tending to infinity, right? It's tending to infinity at z equal to z0. So function fz, this mod, is tending to infinity as z is tending to z0 in any manner. Now as phi z becomes analytic, now first part we have proved, second part what we have to prove is, we have to prove the residue of phi of z, right? So third expression is your power series, which is convergent, and Taylor series is nothing but the form of the power series, or power series is the form of the Taylor series. So can I write 3 represents your actually Taylor series? Because phi z is analytic, with that I can say that this series is a Taylor series for phi z. What is your third check? This is your actually a Taylor series. So because it is a Taylor series, so from here I can get the coefficient of z minus z0 the power m minus 1 is equal to phi m minus 1 z0 over m minus 1 factorial. This is from the definition of the Taylor series, and also I have put this in my remark at the very start of the video. But also if you check the coefficient of z minus z0 the power m minus 1 is equal to what from 3? Check this. What is the coefficient of z minus z0 the power m minus 1? This b1, right? So from 3 I am having the coefficient of this to be equal to b1, and right, so therefore because both are the coefficients of, this is also coefficient of z minus z0 the power m minus 1, this is also the coefficient of z minus z0 the power m minus 1. So can I write both to be equal to? These both are equal. That means phi the power m minus 1 z0 over m minus 1 factorial is equal to b1, which is residue at z0. Hence proved. This is your second part, which is proved now, right? And if you say in particular when z0 is a simple pole, now here z0 is a pole of order m. What if the pole is a simple pole? Simple pole means having the order 1. So if when z0 is a simple pole, then residue at z naught is phi of z naught is equal to limit z tending to z naught z minus z naught the power, sorry, it's not power, it's z minus z naught fz, right? You know that phi of z naught is equal to this. So because the simple pole, the pole is of order 1, which means you don't have rest of the terms over here. If you take your fz, we are having only the term b1 over z minus z naught as your principal part, right? Because pole is of order 1, that means the power 1. The rest of the terms will not be there. Up to only this term we are having. These two terms, right? And when you judge, when you observe, you will get in the conclusion that when z naught is a simple pole, then the residue at z naught is phi of z naught equal to limit z tends to z naught, z minus z naught f of z. Right? So this, just take this as your remark. So this is here ends up the proof. We have proved that phi z has a removable singularity at z naught, right? And also secondly, it is having residue at z naught which is equal to b1 which is equal to phi the power m minus 1 z naught over m minus 1 factorial. Thank you for watching this video. I'm very glad to have my videos for you.